Section 2.5 goes over the transformations in the graphs of functions. To start, here are a few common functions we're going to be looking at transformations for. The constant function, the identity function, the absolute value function, the standard quadratic function f of x equals x squared, the square root function, the standard cubic function f of x equals x cubed, and the cube root function f of x equals cube root of x. So to get a sense how these transformations work, we're going to be looking at these three functions: absolute value of x, and then f of x equals absolute value of x plus 2, and absolute value of x minus 3. For the first one, if we were to take the function f of x equals absolute value of x and plug in numbers like -2, 0, and 2, the function would be respectively 2, 0, and 2. With the same x values in the other function, we get 4, 2, and 4. What this means is the y values have been increased by 2. And as far as the graph goes, that means it'll be shifted up by 2. So we can see that here in the graph how it starts in one location and then it shifts up 2 units. Similarly, for absolute value of x minus 3, with the same values of x, we would get -1, -3, and -1, which means all the y values have been decreased by 3, and that means it shifts down 3 units. So we can see the original graph and then the shifted graph of f of x equals absolute value of x minus 3. Things are a little different though if we do addition or subtraction from within inside the function. So here is f of x equals x to the third and f of x equals x minus 1 all raised to the third. If I use some values for x and plug them in and get f of x, and then I do it for x minus 1 raised to the third power, we can see how the numbers shift over, but in this case the y values are shifting over to the right by 1 unit. So what that means for the graph is it does shift over to the right because of the x minus 1. So we can see that here in the graph how it starts in one location and then moves over horizontally to the right by 1 unit. If we look at x plus 1 raised to the third in comparison, the y values are now actually shifted over to the left by 1 unit. And we can see that in the graph as well. So for x plus 1, we actually have a horizontal shift toward the left by 1 unit. Transformations also happen because of negatives in the function. For instance, if we take a look at f of x equals square root x and f of x equals square root of negative x. And if I plug in 0, 1, and 4, I get out respectively 0, 1, and 2 for f of x. But in order to calculate the square root of negative x, I actually have to make the x values negative. Then I would get out the same y values. So the x values are now negative for the same y values. That means we reflect around the y-axis. So it flips around from one side to the other side for the graph of f of x equals square root of negative x. If I put the negative on the outside of the square root, using the same values as before, now we'll notice how the y values will change to negative. That causes reflection about the x-axis. So from one side of the x-axis over around to the other side. Multiplication causes transformations as well. So here we can take a look at f of x equals x squared and f of x equals 2x squared. If I plug in 0, 1, and 2, it would turn into 0, 1, and 4 for f of x. With 2x squared, however, the numbers are going to be doubled. So doubled the y coordinates, and that causes the graph to have a vertical stretch by a factor of 2. So we can see from the original parabola, it gets stretched upward by a factor of 2. For the 1/2 x squared, what will happen is the y values will get halved. And by halving the y coordinates, that's going to cause a vertical shrinking by a factor of 1/2. So we can see the graph is going to get kind of compressed downward by a factor of 1/2, causing the vertical shrink to occur. Here's a summary of the transformations then from what we're seeing so far. For shifting up or down vertically, f of x plus c would shift up by c units. F of x minus c would shift down by c units. Horizontally happens when the plus or minus addition subtraction happens inside. For instance, f of x plus c would actually move it to the left by c units, and f of x minus c would move it to the right by c units. Reflections happen when we put a negative outside or inside. So negative f of x would cause it to be reflected about the x-axis, and f of negative x would reflect it about the y-axis. Shrinking or stretching can happen vertically or horizontally. Here it shows how stretching happens vertically when c f of x, c times f of x in other words, if c is greater than 1, and it shrinks vertically if the number for c is between 0 and 1. So really fractions, stuff like that, like 1/2 or 1/3, cause it to shrink vertically. On the other hand, horizontal stretching would occur if the number is between 0 and 1, but it actually shrinks horizontally for f of c of x if c is greater than 1. Stretches horizontally for f of c of x if 0 is less than c less than 1. There is an order of transformations listed here. We need to follow this order in the case where there are multiple transformations happening. So horizontal shifting comes first, then stretching or shrinking, then reflections, and then finally any vertical shifts would come last. So here we're going to look at a function that has multiple transformations involved, and we're going to sketch the graph by hand. Here there are two transformations, one due to the negative x and another due to the plus 1. The negative x is going to cause it to reflect about the y-axis. The plus 1 is going to cause it to shift horizontally to the left by 1 unit. We look at the order these need to come in. It says that horizontal shifting has to come first, and then reflections would come after that. So in order to sketch the graph of this one, we can start by looking at what the square root function looks like normally, without any transformations involved. By default, the graph of the square root function does something like this. Now, if we follow along the transformations, we first have to move everything over to the left by 1 unit. So as a result, the points would go somewhere along here. And then, that's shifting left by 1 unit, then we have to reflect it about the y-axis, which means all the points are going to be reflected from one side to the other of the y-axis. So now we would get points that go something like this. So that last graph would be the graph of h of x equals the square root of negative x plus 1. Here's another one that says g of x is equal to 2 times the absolute value of x plus 3. There are two transformations here as well. The 2 in the front is going to cause it to be a vertical stretch. by a factor of 2. The plus 3 is going to cause another horizontal shift, but because it's a plus 3, it's going to move it to the left by 3 units. If we check the order, the horizontal transformation would come first and the vertical transformation would come second. So what we'll do is double check what does the absolute value function look like normally. It passes through points like so, without any transformations involved. So we're going to shift everything over first off by 3 units, over to the left, like so. And then we need to do the vertical stretch by a factor of 2. In essence, what that does is it takes all the y coordinates and makes them twice as big. So points that were at one location get moved upward by a factor of 2. So our final graph would do something like this. So our final graph would be for g of x equals 2, absolute value of x plus 3. Now for the next one we're going to look at is f of x equals negative x minus 3 all raised to the second power and then plus 4. So we have actually 3 transformations at work here. And the order of the transformations would go like this. And the first is going to be the horizontal transformation that is from the minus 3, which is actually moving it to the right by 3 units. And then we have to do any reflections. In this case, we have that negative out in front, which tells us we need to reflect about the x-axis. And then finally, we have the plus 4, which is a vertical shift, which moves it up by 4 units. So several transformations are involved with this one. Let's see how it's going to go. Let's take a look at the basic x squared function, which is the parabola. Looks something like this. So first things first, let's move that to the right by 3 units. So that'll place it over here somewhere. And then we have to reflect and shift up by 4. Now, to save some space here, I'm going to go ahead and do that in one step. If we reflect, basically it would go down like so. But then we have to shift that up by 4 units. So when we're done, it should be positioned somewhere in this vicinity. So what we're going to do on this thing is actually look at the graph of f of x, but try to produce g of x based off of the transformations. The first one's saying that g of x is equal to f of 2 times x. And what happens in this case, if you see the 2 times x inside the function multiplying it, we check with that transformation. That's the horizontal shrinking situation. Horizontal shrinking happens when the number is bigger than 1, like a 2 or a 3. But whenever it shrinks, it's going to shrink by a factor of 1/2. So what we're going to do in order to accomplish a horizontal shrink by a factor of 1/2 is we're going to take all the x values and take 1/2 of them, leaving the y values the same. So looking on the graph, the point here that's at -2, 0 is going to shrink in to -1. 1, 2 is actually going to shrink in here to the point 1/2. comma 2. And this point's going to stay the same. We're going to have a similar shrinking factor on the other side as well. So shrinking it by a factor of 1/2 would cause it to do this instead. So we took, again, 1/2 of the x values, leaving the y values the same, and it shrinks it in horizontally. Now looking at the next one here with the f of 1/2 x, that's actually going to refer to a horizontal stretching factor of 2. So in order to make that happen, we're going to double the x values at each coordinate. So in the original graph, again, we had a coordinate of -2, 0. That's going to stretch out now to the point -4, 0. And this point down here, that was at -1, -2. That's going to stretch out to the point -2, -2. And so we're going to see a similar pattern show up on the other side here as well with those coordinates, as it stretches it outward horizontally by a factor of 2. On this one, it says we're going to graph g of x by using the graph of f of x. G of x is negative f of x minus 1 plus 1. We notice that there are actually 3 transformations here to take care of: a horizontal transformation, a reflection, and a vertical transformation. So the first transformation would be to move it, because of the -1, that's going to move it to the right by 1 unit. The second transformation here would be to reflect, because of the negative out in front, and that would reflect it about the x-axis. And then finally, the third transformation would be the vertical transformation to move it up 1 unit. So let's go through the steps one by one. We'll move it over to the right. We have the points, so we can move all the points over to the right by 1 unit. Then what we can do from here is do the reflection. So we have to take all the points and flip them around from one side to the other. And if we do that, the graph will now be down here instead after reflection. And then we have to move everything up by 1 unit. And that will generate the final transformation of the graph.